do. Spoiler, it's not that much different than recursion part one, right? Because recursion is a consistent concept that we already kind of got the basic building blocks off of. Alright. So doing right. So really, like one thing that we've seen doing the first batch of recursion problems is essentially is what we're doing is we're basically taking a problem and doing smaller and smaller and smaller chunks of it until we get to the smallest possible chunk, which in most cases is our base case. Right? Like that's pretty much all there is to it. Right? Like the point of recursion and the reason why recursion has to end is because we're moving in a direction in which it has to end at some point. And so that's why people like recursion is because it kind of breaks the problem down into its most fundamental level, right? So to Justin's earlier question of like, well, like if I want to count a vowel, it's like, well, all you really need is a string, right? You don't need anything else to tell me how many vowels are in a particular string, right? So that's why like we're breaking it down and we're only kind of keeping what's required. The new concept that we're going to talk about here, and I say new very loosely because it's the same concept we've been talking about, it's just used in different ways. So far, things that most of the problems that you have done today with recursion, we can probably do with a for loop, right? We can do it iteratively. It's not that difficult. But there's a class of problems that recursion is particularly good for that we can't do with for loops, and those are things that we don't know how many times it will take, right? And so now we're actually going to talk about a problem that I wouldn't say haunted, but we've definitely kind of broached before. So like, hey, how do I flatten a nested array, right? If I know the array only has max one level of nesting, I can just use a for loop that goes in twice. But if I don't know how nested an array is, I need something that can just indefinitely go into each successive layer and layer and layer and layer until it reaches the end, right? If I try to do that with a for loop, I can write 6 layers of for loops, but if there's a 7-layer nested array, then my function breaks, right? Recursion doesn't have that limitation because recursion will just say, yeah, I'm just gonna keep going until eventually I reach the end, and then I'll stop. And so for that reason alone, recursion is really good for problems in which we don't know how many times we need to do it, or how deep we need to go, or how many times the function is going to be called. So this is just a really bad implementation of how you would write a nested array parser with a for loop, right? Like, and even then, we don't actually know if that's enough loops, right? We only did 4 there, or 3 there. What if there's 4 nested loops? Then we're kind of screwed. So this is the recursive solution, right? Where we have our base case, which is, hey, if the array is empty, just return nothing, right? We don't need to return anything. But otherwise, if it's an array, all right. If it's an array, then call it on itself. And then if it's not an array, let's just log it out and then try to figure out what the rest of the thing is. I actually don't. I think this code won't work. Or rather, this is not probably the best example. But the point here is just to say that like this bottom half of this code down here is like how we want to be thinking about it, right? Which is like, hey, like if you're an array and your child is an array and your child's child is an array, and so on and so forth, like recursion doesn't care. It will just kind of keep doing this, right? And either you break or the computer breaks, right? So if you have like a 6 trillion nested array, yeah, you might break JavaScript, so to speak, but then it's like, what are you doing? Right? So within the confines of reasonableness, like recursion really does do a really good job of hunting for answers when you don't know how deep or kind of where the answer is. Yeah, so indefinite operations we call them, and recursion is really great for that, right? It's similar to a while loop, right? If I had to roll a die and get a 6, if I cap my for loop at like 1,000 and I roll my die 1,000 times, I'll probably get a 6. But a while loop will, guarantee that I get a 6 eventually, right? So will recursion. The only difficulty there is, like recursion obviously, could go bad really poorly, and so we also talk about, well, actually, in the next time we'll talk about kind of the drawbacks of recursion. I think a lot of those you guys have already encountered firsthand here. But so when do you use recursion? Recursion is harder than looping, like straightforward loops. There's no denying it, and recursion is one of the things that like, people test a lot about in job interviews, but I've actually probably written like very few truly recursive things over my like various jobs. And the reason why is because they're hard to understand, they're hard to maintain, and a lot of times you can do the same thing with a normal loop, right? So for now, we're teaching you how to use recursion. So that's why we're making you use recursion. But in the real world, like as with anything else, use the tool that's best for the job. If it takes you 6 hours and a lot of risk to write a recursive loop, and it takes you like 5 minutes to write a for loop, just write a for loop. So the things that recursion is good for. Iterative branching, that's just like traversing a nested, indefinitely nested for loop, or sorry, an indefinitely nested array is really good at that. Sorting, you'll implement this, so I won't talk too much about it, but you'll see how recursion is actually really great for sorting too. And then the third one is very, very similar to number one, except rather than nesting, if it's like a bunch of relationships or connections, or like graphs, recursion is also really good for that, but we probably won't touch that too much, right? Conceptually, it's the same exact thing in terms of how recursion works for all of these. So once again, recursion, right? Left-hand side, recursion, right hand side, for loop. They both do the same exact thing, and in this case, if you're better off doing a for loop, do a for loop. But this is to show you that like recursion sometimes can. There are scenarios in which recursion can do things that you can't do with a for loop or wouldn't want to do with a for loop. And this is this probably harkens back a little bit to yesterday when I made a scene about using returns, right? And it's like, and this is why like returns are now more critical than ever, because before you just had one function, it ran, right? And so you're like, oh, if a console logs it, if it returns it, so what? Doesn't really matter. Well, now you have functions calling other functions, and depending on the values of those functions to do its job, right? And so now if you're not returning correctly, you're going to break one of those functions, and then your whole thing's going to kind of collapse on itself. So as we move further and further away from just kind of running one function, having a human proofread the results, to the world in which computers and functions are calling each other and working with each other, the returns are super, super critical. And so this is a reverse string array. I won't go into this because this is effectively the same thing as the reverse array problem that we just walked through together. Same idea. As you can imagine, strings and arrays, not that different from a use standpoint. But if we didn't do, or rather, like here, what they're doing, let's see, this solution is probably what Chris and Lawrence did, right? Like they start from the end and work their way backwards. Equally valid. We could start with the H and work our way backwards too. Doesn't really matter, right? So we just animation, ta-da, and then we return back, right? If you want to draw a stack and walk through this, feel free to do it on your own, or we can do it together as a group, kind of once the workshop starts. But like, you should nothing I'm saying here should be like practically new. Maybe it's like one or two new ideas of how to apply concepts, but like. Once again, this is the same exact recursion that we've done all morning, so nothing's changed. And once again, write a recursive function. Be super clear about your base case. Define your recursive case. When should the function call itself? And let's just put in here also, what are you returning, right? Like if you're in your base case, you should be returning something. In your non-base case, you should probably also be returning something, right? Because someone's calling that recursive function, so they expect something back. Right? They're not just doing it for their own health, right? Like if your length is 0, give me back 0. Great. If your length is not 0, well, you gotta give me back something, right? Otherwise, like, why am I calling you? So just be careful about your return cases too. That's pretty much it. So like I said, recursion part 2, not too much new stuff, just more practice with recursion. Any questions? We good?
What was conceptually introduced that was new in this lecture?
I'm sorry?
Was anything new? Were any new concepts introduced?
Oh, I mean, I would say that so probably not this is more practice for you guys, but I would say the only kind of conceptually new and not practically new is practically you're writing the same code. Conceptually, it's just the idea that there are a certain class of problems that can only be done with recursion, but not iteration. I think in the last set of problems, everything there could have been done with iteration if you really wanted to.
Sure.
That's pretty much it.
When we're doing that assessment, will it require us to use recursion to solve problems?
Yeah, so usually, at least when I personally gave interviews,